Today would be lecture 18, I think. Yeah. Okay, so welcome back. Let me, welcome back. So today we will start lecturing from chapter 1, 2, 3. We have done 4. We are skipping from chapter 5. And we want to do Dirichlet's unit theorem, which I will not get into today, but there's a preparatory result which I will do today. Okay, so let me start sharing the screen. So can you confirm that you can see the slides?
Yes, we can see.
Okay, so let's start. It is what I'm titling as towards the unit theorem. So unit theorem we saw in our discussion class on Monday. And anyway, I will state it formally in my slides and we will come back to it. But today we will not state it. Today we are going to do a volume computation with the aim of doing the unit theorem. Okay, so I'm not recalling anything from the previous classes. All those are done, and we are starting a new chapter. And please pay attention. I mean, these are all easy things, but it might look like a different language. Okay, because we are going to club global theory and local theory together. It might look like a different language, but there's not much in it if you pay attention. So this is where we started, right? We started with the very first lecture of this course had absolute values on a field, and we had the Artin-Vapers approximation theorem, and all those ideas will be used today. Okay, so what do I mean by, so K is a number field, finite extension of Q, and you know that you have absolute values. You have so many absolute values. How do you get a typical absolute value? You can embed it in R or C, and for each embedding you can take the real absolute value or the complex absolute value. Those are the Archimedean absolute values, and then you have the non-Archimedean absolute values. What do? You take the ring of integers, you take a prime ideal, you know that it's a Dedekind domain. You take a prime ideal, and that prime ideal gives rise to an absolute value. So those will be the non-Archimedean absolute values, so the discrete absolute values. And what do I mean by the canonical set of absolute values? For each prime, we are fixing a normalization. We are fixing, so the absolute value of x is c power r, where c is between 0 and 1, and r comes in the, r is the periodic valuation. And what is C? The choice of C is 1 by norm of the ideal. So if P is your ideal, norm of P, where is norm? Norm is from K to Q. Now, throughout, when we take a number field K, the base field is Q. So norm is norm from K to Q. So norm of this ideal in OK will be a prime ideal in Z, which is of course Z is a PID. It will be generated by a usual prime number. Okay, so canonical set of absolute values is with respect to this normalization, the constant between 0 and 1, we are choosing it to be 1 by norm of P. So what is norm of P? Norm of P is if small p is the prime number lying below the prime ideal P, then norm of P is P power the residue degree F. So it is nothing but take the residue field, take the cardinality of the residue field. That will be the normalization. And with respect to this, in our discussion class, we saw the product formula. Of course, we did not fully prove it because it assumes something from chapter 2, which we did not do. But still we saw it's not a very difficult thing. There is the product formula, which we will use today. So K is a number field, and Mk is the set of this canonical set of absolute values. So there are the Archimedean absolute values and there are the non-Archimedean absolute values. Non-Archimedean absolute values correspond to prime ideals in OK. One prime ideal, there is a natural one absolute value corresponding to it. Okay, and then there are the infinite absolute values, so the Archimedean absolute values. MK is this collection. And we are going to define the concept of an MK divisor. So what is it? It is a function on the set of absolute values, on this canonical set of absolute values, and it is real valued, it's positive real valued. And let us say what it is. It is a function on MK taking values in real numbers which satisfies three properties. First property is that for each V it is positive. Okay. For whatever absolute value you take, Archimedean or non-Archimedean, infinite or prime, this function attaches a positive number to each absolute value. For almost all absolute values, it is 1. Almost all meaning except for finitely many. So CV is always positive and it is almost always 1. Except for finitely many absolute values, it is 1. And there is one more property, which is that for every non-Archimedean absolute value, for all discrete V, this value has to be mod alpha V for some alpha. So corresponding to C, there exists an element alpha in your number field such that its V-adic absolute value mod alpha V is CV. Okay. So an MK divisor is a function which satisfies these three properties. So can you give an example of such a function?
Constant function 1.
Constant function 1, yeah, constant function 1. The first property is true, it is positive everywhere, and it is 1 almost always true. So what will you choose as your alpha so that CV is mod alpha V for all discrete V? It's alpha V1, right? So
Yes.
mod 1 is 1, yeah. So that's an example. And you can generate more examples. What you can do is you can take any. So you took the element 1, right? You took the element 1 and you just took its modulus with respect to all the V, and you got the constant function 1. So that's correct. Instead of 1, you can take any element of your field. If you take alpha in K, and if you take the function V going to mod alpha V, fix an alpha, and take the function V going to mod alpha V, that satisfies all these things, right? So third condition is automatically satisfied, and first condition is automatically satisfied because mod alpha V is positive for all V. And what about the second condition? If I fix an alpha and if I take mod alpha V, is it true that it is 1 for almost all V? It is true, right? Because so you take the ideal generated by alpha in its prime factorization, only finitely many prime ideals will come. So for all the other prime ideals, mod will be 1. You agree? Suppose you take mod alpha V and you take the ideal generated by alpha, do its prime factorization, except for the primes coming in its, that will be a finitely many primes coming in there. Except for those finitely many primes, at any other prime, what will be the absolute value of mod alpha with respect to any other prime not coming in the factorization? It will be 1, right? Valuation will be 0. It's not appearing in its factorization. So valuation will be 0, and that means absolute value will be 1. So these are the basic examples. You fix an alpha in K and take mod alpha V going to mod alpha V for the fixed alpha. So more generally, at the Archimedean places, you can prescribe any other number, any other real number, and those will be extra functions like this. Okay, so those are all MK divisors. So for P contained in OK, we have the obvious notion of order of C at P, which is what? Because if P is contained in OK, for all discrete V, it is given by an alpha, no? At discrete places, this is given by an element alpha. It is just mod alpha V. Only at the infinite places, only at the Archimedean places, there could be some deviation. And so what is this notion? For a finite prime P, The obvious notion of order at C at P is the order of alpha at P. In the factorization of the ideal generated at alpha, to what order, to what power the prime ideal P comes, that we call the order. Okay, so which is order of alpha at P. So we have this notion. And note that this remark we already said, alpha in K star defines an MK divisor given by alpha of V equal to mod alpha V. And clearly product of two MK divisors is an MK divisor. Agree? If there is C1 and C2, C1 of V is 1 almost all the time, C2 of V is 1 almost all the time, then the product is 1 almost all the time. Product of positive is positive. And if C1 is given by alpha 1 and C2 is given by alpha 2 at all the finite primes, and C1, C2 is given by alpha 1, alpha 2. So product of two MK divisors is an MK divisor. Now some more notations. I'm going to define the norm of C at V. At V, the norm of C to be, you have CV and you raise it to the power NV, where what is NV? NV is the degree of the completions. So at V, if you complete K, you have the complete field KV, and V lies above some absolute value V0 of Q, and you complete Q at V0. So KV contains QV0, and that degree, the local degree, is called NV. So this CV power this NV has this notation norm C with respect to V, and V is something V extends V0. V0 in MQ and V in MK extends V0. Okay. So mod X subscript V is mod X subscript V0 if X belongs to Q. Extends. And you have the product formula, which is also called the Artin-Wapers product formula, which we saw in the discussion class, the statement we saw, which says that the product over all the absolute values and the norm of alpha, this product is 1. So for Q, it is obvious. And for a number field, by taking norm, we can come down to Q and use the formula for Q and use the relationship between norm, and that will raise to the power of NV. And this proves, so the usual proof for Q together with one more fact proves this formula, and that fact is from chapter 2, which I highlighted in the last class. We didn't give the full proof, but I highlighted it, which is that the relationship between norm alpha and alpha, between absolute values. What is the relationship? It is that modulus of norm alpha, let us say modulus with respect to V0, is equal to product of alpha, modulus of alpha with respect to V, where the product is, it's a finite product, V lying over V0, V extending V0. So once you have this formula, and you have the product formula over Q, which is obvious, then you have the general product formula. Okay, anyway, assume the product formula. Product of norm alpha V as V varies is 1. And norm alpha V is nothing but mod alpha V power NV. The normalized mod is norm for alpha in K star. Okay. Now we are going to define the K size of C, or the size of C. So given an MK divisor, there is a notion of its volume. Okay. And this is defined as, this is a notation, norm K norm, K size, the volume of it is product over all the absolute values, and you take the norm V and take the product. So as we said, alpha gives rise to an MK divisor, and product of two MK divisors is an MK divisor. And if you take the size of it, it is same as this, because the size of this will be product of the size of alpha times size of C, and size of alpha is 1. Size of alpha is 1, and that is exactly the product formula. Okay, therefore the size doesn't change if you multiply a given divisor with the divisor coming from alpha in K star, what is called a principal divisor. Okay, Principal divisor, just like a principal fractional ideal, principal divisor is a divisor coming from a global element, alpha in K star. So this is by the product formula. Okay, so some number of notations here, and now we are going to consider this set. So given an MK divisor C, associated to it you have this set L of C, which is all those elements from your field K, such that all those elements from your field K such that mod x V is less than or equal to CV for all V. For all the absolute values, if you take its mod V, that should be less than or equal to CV. Okay, so this is some set, and we are interested in the cardinality of this set, and our main result is going to be giving some inequalities for the cardinality of this set, one upper bound and one lower bound. That's all that we will do today. So let us denote the cardinality of this set by lambda c, and the main result that we need to do today is to get an approximate value for lambda c in terms of an upper bound and in terms of a lower bound. Now note that if you take alpha in K star, lambda of alpha c is equal to lambda c. Why is that? Because L of C and L of alpha C are in bijection, right? Same cardinality means bijection. L of C and L of alpha C are in bijection. Can you give the obvious map from L of C to L of alpha C? So L of C consists of x in K such that mod x is less than or equal to CV. L of alpha C will be those x in K such that mod of alpha x V is less than or equal to
Alpha, multiplication by alpha.
Yeah, multiplication by alpha. So this is the obvious map from LC to L alpha C given by multiplication by alpha. So if you take alpha x, then that belongs to alpha C, right? Alpha x, mod alpha x will be mod alpha times mod x. And if mod x is less than or equal to CV, mod alpha x is less than or equal to alpha C at V. So there is the obvious bijection, and therefore these two sets have the same cardinality. Now this is a picture to keep in mind. An MK divisor C, you should think of it as an infinite cube. Okay, infinite cube. So almost all the sides, what is the length? So C is an infinite cube parameterized by absolute values. The sides of the cube are in 1-1 correspondence with absolute values, canonical set of absolute values. And almost all the lengths, what can you say? Your second condition, CV is 1 almost all the times. So almost all the lengths are 1. Some number of lengths need not be 1. And that is your infinite cube. And what is L of C? L of C is x in K such that mod x V is less than or equal to CV for all V. So these are the points from your field which are inside this infinite cube. So L of C are field elements of K inside this cube, and you are interested in its cardinality. Okay, lambda C is the number of elements of K inside this box. So think of the K size of C as the volume of this box. Okay, so how did we define C? K size? It is product over all V of norm of alpha. In other words, mod alpha power NV. NV is the degree. So you can think of that as the correct definition of volume. And maybe in some elementary mathematics you have seen this thing, right? If you have a grid, say on the plane, if you have a grid, then if you have a lattice, right? Then there's this philosophy, right? Number of lattice points is roughly what? It's roughly the area, right? So so this kind of a thing, in many, properly phrased, this kind of a thing will come in various contexts. That's what's coming here also. We are going to precisely state that. So the first result is that the number of elements lambda c is roughly the volume, where volume we have defined like this. Okay, so this is what we should prove. So here is a statement. Lambda c is roughly the volume. What do we mean? This is the claim. There exist two constants C1 and C2. Both are positive constants These constants will depend only on the number field, on nothing else. They depend only on k such that lambda c, which is what we are interested in, number of field elements inside this infinite box, this is strictly bigger than C1 times the volume of the box, and it is less than or equal to C2 times the volume of the box. So there are two constants C1 and C2 such that the number of field elements inside is bigger than the volume up to one constant and less than the volume up to the other constant. This is the claim, and this is useful in proving the unit theorem. Okay, so we are doing this in order to prove the unit theorem, maybe in the next class. This is true for any MK divisor C. So whatever MK divisor, the constant C1 and C2 do not depend on the divisor C. The constant C1 and C2 depend only on the field K and on nothing else. That's the important thing to see. Okay, so let us prove first this inequality, the right hand side inequality, which is slightly easier, and then the left hand side inequality after that. Okay, and then we will stop. So let's prove this first, and I'm going to assume that there is at least one complex absolute value. If not, proof is more or less the same, but notationally there's a difference between complex absolute value and real absolute value, and therefore let us assume that there is at least one complex absolute value. Call it V naught, at least one. Okay, so pick one, call it V naught. So if you complete it with respect to V naught, then you are getting a copy of C. Okay, because it's a complex absolute value. So when you complete, you are getting C. So identify KV naught with C. KV naught, think of KV naught as C. Okay, so it's a plane. C means it's R2, right? It's a plane. It's a complex plane. And now you consider the square centered at the origin with sides of length twice CV naught. So you have chosen this V naught, and C is given to you. The theorem is for a fixed C. So CV naught is some positive real number. Take twice CV naught and take the square. So it's not the unit square, but the square centered at the origin. You can picture the square. Each length is twice CV naught. Take the square. Okay. So this was the definition of LC, and lambda C is the cardinality of this set. LC is x in k such that mod xv is less than or equal to cv for all v. So what can you say about points of LC? If you have, so mod x is less than or equal to cv for all v. In particular, mod x v naught is less than or equal to cv naught. So what can you say? LC is contained in this square, right? Because this square has length 2cv naught. So that means above the origin in the positive direction it has length cv naught, and down again 1 cv naught. So any point inside this square, its complex absolute value will be less than or equal to cv, right? Cv naught. And by definition, LC has the property that any element in LC has all the absolute values less than or equal to corresponding CV. In particular, at CV naught mod x V naught, which is a complex absolute value, usual complex distance, this is less than or equal to CV naught. So this square that we have constructed, the set LC is contained in this square. You agree with this? LC is contained in this square. We are interested in proving this inequality. Number of points inside that, the cardinality of LC is bounded by supremum of 1 comma C2 norm CK. We want to prove it's bounded by C2 norm CK. You will see why supremum 1 has come in. Okay. Now let M be an integer such that, so whatever lambda C is, you take its square root, and that square root lies between m and m plus 1. M strictly less than lambda C square root less than or equal to m plus 1. Choose such an m. Now if m is 0, then you know that lambda C is less than or equal to 1. So that's why I have put supremum of 1 comma something. So if m is 0, it is less than or equal to 1, and therefore you already have this inequality. So assume that m is not 0, and we need to prove that if m is not 0, we are going to prove that lambda C is less than or equal to this. Therefore this is proved. So this supremum 1 I have put, and I'm going to assume m is bigger than or equal to 1 without loss of generality. Because m equal to 0, you already know that lambda c is less than or equal to 1. Trivially. So assume m is bigger than or equal to 1. Now that m is at least 1, it's an integer. You divide this square that you have considered of length 2cv naught into m square smaller squares of equal size. Make a grid like in various, make a grid of equal size. So what you're doing is take the length, cut it into m equal parts, take the width, cut it into m equal parts, make those squares. So you have got m square squares equals squares of equal area. And lambda c is bigger than m square, right? By your choice of m, lambda c is bigger than m square, and you have cut this into m square squares, and the cardinality is bigger than m square. So what can you conclude? You can conclude that there are two elements in your set LC which belong to you have m square number of squares, small squares, and your set has cardinality bigger than m square. So by Pigeon Hole, at least two elements belong to of your set LC belong to one small square. There exists x and y in LC such that they belong to the same small square. And if you have x and y in one small square, what can you say? You know that its distance, this is a complex absolute value. So the usual distance between x and y, what can you say? It is less than or equal to root 2 times the length, right? If you have the unit square and if you have any 2 points there, the obvious bound, the distance between that is less than the diagonal, which is root 2. So root 2 times the length. Length is 2cv0 by m. So mod x minus y at b0 is less than or equal to length times root 2. This you know by Pigeon Hole. For v not equal to v0 also, let us compute mod x minus y v0. So for v not equal to v0, what can you say about mod x minus y v0? Suppose v is non-Archimedean. You have the triangle inequality. So mod x minus y is less than or equal to mod x plus mod y. And what do you know about mod x and mod y? Mod x is less than or equal to, these are x and y are from LC. And LC is mod x is less than or equal to CV. Mod y is also less than or equal to CV. So mod x plus mod y is less than or equal to twice CV. So if this is Archimedean, it is less than or equal to twice CV. Otherwise also twice CV, but you can make it in fact CV because mod x minus y is less than or equal to maximum of mod x comma mod y. Ultra metric inequality. So it is less than or equal to CV. Agree? You have these things. Therefore, if you take product of mod x minus v, x minus y v power nv over all v, on the one hand this product is equal to 1, right? Because x minus y belong to k. And Artin-Vapel's product formula says that if you have any alpha in k, then product over v mod alpha v power nv is equal to 1. This you know. On the other hand, because of all these inequalities, when you take the product, what do you get? You are getting this times twice CV times CV as V varies. So what you are getting is product of CV as V varies, which is what we call product of CV power NV, which is what we call the size of C. Size of C is exactly product of CV power NV. That is the definition, right? What is the definition of size of C? Size of C is product of CV power NV. CV power NV. That is what is called the size or the volume. Okay, so you've got some constant times the volume of C by m square. Why m square? So you are multiplying CV0 power NV0, CV power NV, CV power NV, all those together gave you the size of C. And what is this constant C3? This constant C3 is 2 root 2 times 1. This is where you know this is 1 is important because it's an infinite product that you are taking. And an infinite product makes sense only if all but finitely many terms are 1. So therefore this 1 was useful. So at all the Archimedean places, either 2 or this particular place 2 root 2 you multiply. So that's a finite number. That's some power of 2 times root 2. Finite power of 2 times root 2. So that is a non-zero constant. And that depends only on k, right? C3 depends only on k. Why? Because it is 2 power number of Archimedean valuations times root 2. And how many Archimedean valuations are there? It depends only on k, nothing else. So C3 is a positive constant depending only on k times the size of k. Why m square? Can someone tell me why m square? Because it is this power nv. So m power nv. So nv is 2, right? Nv naught is 2. Why is nv naught 2? Because what is nv naught? NV naught is you complete and you take the degree of the extension. So Q if you complete you get R, and K if you completed V naught, what do you get? You get C. So the NV naught is the degree of C over R, complex numbers over real numbers. That is 2. That's why this is M square. Okay, and this gives lambda c less than or equal to, you know from this inequality that lambda c is less than or equal to m plus 1 whole square, but by your assumption m is bigger than or equal to 1, therefore m plus 1 is less than or equal to 2m, so this is less than or equal to 4m square. But what you have proved is m square is less than or equal to c3 times the size of c, so this is less than or equal to 4c3 times the size of c, and you can call c2 to be 4c3. So that proves this, right? Because if m is 0, then it is less than or equal to 1. Therefore, you can assume m is not 0, and then we proved that it is 4c3 times the size. 4c3 you call c2. That's a positive constant depending only on k. This was under the assumption that there is at least one complex absolute value. Suppose you don't have a complex absolute value. Like if you take q root 2, there is no complex absolute value. Both the Archimedean absolute values are real. If that is the case, then if there's no complex absolute value, you can argue similarly. Just for notational purposes, I fix complex. You proceed by arguing with a real absolute value V naught, but real absolute value is in real line. So you don't have a square. So instead of a square, what will you consider on the line? You consider a line segment centered at 0 and of length 2 CV naught, exactly like earlier. And this time you will cut it into m equal size and you will argue with those subintervals. But that m you should choose so that m is less than lambda c less than or equal to m plus 1. Earlier you took lambda c square root because earlier it was complex absolute value, there was a square involved, and for that you took the square root here. Now you take lambda c such that there is no lambda c between m and m plus 1 and cut this interval of length into m equal parts and argue exactly as before. Same proof goes through. So here you will get m, and here you will get m, not m square but m, because nv naught will be 1, because qv naught is r, kv naught is also r, so r over r degree is 1. So here you will get 1, and that is okay because anyway you have inequality is for m and m plus 1, not for squares. So everything will go through exactly the same proof will work. You will prove this side. So one side is okay, all the arguments will go through. Okay, now more important, slightly more work in order to show the other side. Other side is there is a constant depending only on k, positive constant, such that lambda c is strictly bigger than c1 times the volume of c, c1 times the size of c. Okay, and the main idea here is Artin-Vepel's approximation theorem that we have stated and proved in the very first lecture. Okay, so the importance of doing all those things is coming in proper number theory. Okay, so this is what we have to show. C1 times the volume is strictly less than lambda c. Okay, good. So let's do this. So So what we know is that OK, what is OK? The ring of integers. This is the integral closure of Z and K. And we know that it is a free Z module of rank n, which is the degree of K. We know this why? Because Z is a PID. We know that OK is finitely generated and there is no torsion because these are all integral elements. These are algebraic integers. They can't be torsion. And therefore, by the structure theorem for finitely generated modules over a PID, it is free. And then it was easy to check that the rank equal to the dimension of K over Q. So you choose a basis, W1, etc., Wn of this free module OK. And let us take the supremum of mod Wi for the absolute value V as I varies from 1 to n and as V varies from all the Archimedean absolute values. So it's a finite set, you are taking the maximum. But there are only finitely many Archimedean absolute values. In fact, you know exactly how many Archimedean values are there. If K has degree n, then how many embeddings are there into C? N embeddings. So there are n absolute values, out of which the complex absolute values will come in pairs. If a plus bi going to a plus bi and a plus bi going to a minus bi, right? They will come in pairs, and then there will be some number of real absolute values. So V is varying over the Archimedean absolute values and I is varying from 1 to n. You take C0 to be this. I think there is a typo. I also want to put a capital N here. Okay, capital N times this. So I will correct it at the end. Capital N times this. That is my C0. This is a constant depending only on K. Because capital N is the degree which depends only on K. And all these Archimedean absolute values depend only on K. So this is a constant depending only on K. Now recall from lecture 1 the Artin-Vapels approximation theorem. If you have, on any field, if you have S pairwise independent absolute values, and if you give me S elements, then for every epsilon positive, there exists a K, X and K, such that mod X minus Xi at the ith absolute value is less than epsilon. You recall all these things, this is like the Chinese remainder theorem. If your absolute values are non-Archimedean, then this follows from the Chinese remainder theorem. But this result is general because these are for any absolute values, including Archimedean. Okay, this is true for all. Simultaneously, you can approximate. So it's an approximation theorem. And using this, we claim, so this is a claim that I will not prove right now, but assume the claim. We claim that as a consequence of this Artin-Vapels approximation theorem, with the choice of this constant C0, where there's a typo, C0 as capital N times this supremum, you get an alpha in K star. So Artin-Vapels guarantees an alpha such that some simultaneous approximation takes place. You get an alpha in K star such that mod alpha V times CV is bounded between C0 and 2C0. Okay, this is a claim. Let's assume the claim for the time being. So for each Archimedean V, you are applying Artin-Vapels to the collection of, that is, Artin-Vapels you can apply for any finite collection of absolute values. And we are applying it to the collection of Archimedean absolute values. It's a finite collection. Okay, for each Archimedean V, simultaneously you can approximate, you can put this mod alpha times CV is between C0 and 2C0. There is such an alpha. So the claim is there exists such an alpha, says that this is true. Assume the claim and let's continue. Now you pick an integer A, and this integer you are going to pick so that it has very high powers, very high prime powers at enough number of primes. You will see why. Highly divisible at a lot of prime numbers, so that mod A alpha V CV is less than or equal to 1 at all the discrete places, at all the non-Archimedean places. This you can always manage, right? At any non-Archimedean place, CV is given, mod alpha V is given. So mod alpha V times CV will be some number, some real number, some power of P, positive or negative power of P. What you do is, whatever P is coming there, I mean at P, see this alpha is already given to you by Artin-Vapers. Okay, so at almost all the P mod alpha, at almost all the non-Archimedean V mod alpha V will be 1. Alpha will be a unit at almost all the places. So mod alpha V will be 1. CV is also 1 by definition at almost all the places. Okay. Therefore, mod alpha V times CV is 1 at almost all the prime numbers. At almost all the prime ideals, mod alpha V times CV is 1. So those prime ideals, the corresponding prime numbers lying in Z below, you don't bother about A, choice of A. But at other prime ideals which contribute to mod alpha V and CV, at those prime ideals, the corresponding prime numbers lying below, you take sufficiently high powers and multiply them together, you will get an integer A. Such an A, if you choose, what you have done is by having sufficiently high powers of P in it, mod A at that particular P is very, very small. High power of P meaning the periodic absolute value is very small. So by making it small enough, by multiplying by this, you can bring it less than or equal to 1. So this is easy. So do this. Now we have observed earlier that both lambda C and the size of C. So my definition had, so one more typo, there is a subscript K here. So one capital N missing and subscript K here. So lambda C and the size of C, both these do not change if C is replaced by any multiple from K star, right? Lambda C does not change because LC and L alpha C have the same, are in bijection. And this size of C, volume of C does not change because of product formula, volume of alpha is 1. So C replaced by any multiple from K star, these two things will not change, and our inequality has only these two things, right? Inequality was about lambda C and size of C. Inequality is about lambda C and size of C. Lambda C and size of C. So neither will change if you multiply. So without loss of generality, you can multiply by a suitable element. And we are going to work with A alpha C. So this alpha is the alpha from this claim, Artin-Vapers claim, and this A is this A with sufficiently high powers of all these prime numbers so that this property is true. And we are going to work in order to prove this inequality instead of C with A alpha C, and that doesn't matter as these two things will not change. Okay, we are going to work with A alpha C. And therefore, for this new C, so our new C is this A alpha C. So for this new C, we have the inequality. You have A alpha C. Mod alpha times C is between C naught and 2 C naught, and you are multiplying by A also. So it is C naught times mod AV and 2 C naught times mod AV at all the Archimedean places. Agree? So this is what you have. At all the Archimedean places, you have this. CV is between C naught mod AV and 2 C naught mod AV. So let's continue. Now we are going to consider this set, this collection L. So what is this? This A that we have chosen, AI are integers between 0 and A. So A plus 1 many integers. And you consider this is the basis that you have chosen, W1, etc., Wn, and consider integral combinations where AIs are between this. So it's a box inside your ring of integers. Okay, so this is contained in OK. And what can you say about the cardinality? The cardinality of this is actually A plus 1 whole power n, right? Because A1 varies, A1 has A plus 1 many choices, A2 has A plus 1 many choices, etc. So this collection has A plus 1 power n many elements. What we are interested in is this collection has bigger than A power n. It is A plus 1 power n, so it's bigger than A power n. And let NP be the order of C at P. You remember we can define order of C at P. Why? Because C is given by, at each prime ideal, C is given by an element alpha, and order of C is nothing but order of alpha at P. So let's call it NP and consider the map from OK to OK by product of P power NP, the obvious map, the quotient map. And this is the map of additive groups. Okay. As a map of additive groups, we are considering this, and what is the size of the right hand side? What is the cardinality of the right hand side? Can you tell me? By Chinese remainder theorem, OK by product P power NP is isomorphic to product of OK by P power NP. And what is the size of OK by P power NP? What is the size of OK by P? Size of OK by P power NP is size of OK by P power NP. And what is the size of OK by P? By definition, it is norm P. Norm as an ideal. Okay. So the right hand side has cardinality product over norm P power NP. Look, this will be a finite product finally, because NP will be 1. No, NP will be 0. Almost all the places NP is 0. So this is a finite product. Okay, here norm is the norm of an ideal from K to Q. Okay, therefore the conclusion is, under this map you have L, and under this map L is contained in OK, and the image of L inside this has cardinality this much, and this has cardinality bigger than this. Therefore, again by pigeonhole, the conclusion is L has a subset L prime of cardinality at least this much, a power n divided by this product that corresponds to its image here, such that all members of L prime will have the same image under this natural map. This pigeonhole, because this cardinality is something, this cardinality of L is at least this much. So a power n by this cardinality, those many things will go to the same point because of this this map is surjective, because this map is surjective. Okay, so these many, at least these many things of L will go to the same thing, and that is called the set L prime. So L prime, there is a set L prime, all whose elements will have the same image and of cardinality at least this much, because model is bigger than this and the right hand side cardinality is this. Okay, so what does that mean? So now we are going to do fix an x in L prime and vary y in L prime. Okay, but both x and y are from L prime, and you are going to consider x minus y. So x and y have the same image, right? L prime consists of those elements. L prime is one set, and we know the property of that. We know two properties of that set. One, any two elements of L prime will have the same image under that map, and the cardinality of L prime is at least that quantity. So because they have the same image, what can you say? The image of x is x plus product p power np, image of y is y plus product p power np. They have the same image. So x minus y belong to product p power np. But if x minus y belongs to product p power np, what does that mean? That means order of x minus y at p is at least np. Order of x minus y at p is greater than or equal to np. What does that mean? If order of x minus y at p is greater than or equal to np, that means the absolute value of x minus y at p is less than or equal to 1 by norm p power np. Okay, so order is at least order of c. Yeah, so order of or np is nothing but order of c. By definition, I mean NP was a notation for order of C, and this means the absolute value of x minus y is less than or equal to CV, right? Because what is order of C? This is a finite prime. So order of C, P is given by, you know, some element, right? At all the discrete places, CV is, let us say, mod beta, some element beta, so that mod beta power P, and order at C is order at beta. So if order of x minus y is bigger than or equal to order at beta, then mod x minus y is less than or equal to mod beta, but mod beta is CV. So mod x minus y at V is less than or equal to CV. For all the non-Archimedean V, you have got this. Okay, and what about the Archimedean V? If V is Archimedean, then you do the definition of L prime. L prime is a subset of L, and so you use the definition of L. What do you know about the definition of L? L consists of elements like this. X, so that means X is of this form and Y is of this form. So what can you say about X minus Y? X is summation AIWI. Y is also summation AIWI, I mean summation BIWI. So X minus Y is summation AI minus BIWI. What can you say about the bounds of AI minus BI? AI is between 0 and A and BI is also between 0 and A. So what can you certainly say about AI minus BI? It will be between minus A and A. So modulus of BI is less than or equal to A. So if V is Archimedean, then X minus Y is B1 W1 plus etc. plus Bn Wn, with where BI's are integers and BI varying between minus A and A. Therefore, what can you say about mod X minus Y with respect to V? V is Archimedean. That is less than or equal to modulus of this, which by triangle inequality is less than or equal to modulus B1 modulus W1 plus modulus B2 modulus W2 plus etc. But modulus B is less than or equal to modulus A for all B, all the i's. So mod A comes out. Mod A comes out, and what you have is mod W1 plus mod W2 plus etc. But each of this is less than or equal to the supremum of mod Wi. So supremum, if you replace mod Wi by supremum mod Wi, then it will be n times supremum mod Wi, which is less than or equal to C naught. C naught is a constant n times, C naught is a constant n times, there is an n missing here, n times supremum over all V and all I. But that particular element that came there is supremum over all I. In particular, it is less than or equal to supremum over a bigger set. So that is less than or equal to C naught. So mod X minus Y at V, if V is Archimedean, this is less than or equal to this, which is less than or equal to C naught mod AV, but that is less than or equal to CV. That is what we concluded from Artin vapors. Right, you have this C naught times mod AV is less than or equal to CV. Without loss of generality, C has this property. So what you are getting is C naught times mod AV, which is less than or equal to CV. So you have this. This is the definition of C naught. This is by the definition of C naught, and this is by the definition of C. By our choice of C, CV is bigger than or equal to C naught AV. So you have got mod X minus Y at V is less than or equal to CV. You have got at the non-Archimedean places, also at the Archimedean places. So everywhere you got. And therefore you conclude that X minus Y belongs to LC. What was the definition of LC? It consists of all those X and K such that mod X V is less than or equal to CV for all V. What you have proved is mod X minus Y is less than or equal to CV for all V. Therefore, X minus Y belongs to LC. So if you fix an X in L prime and Y varying in L prime, you have shown that X minus Y belongs to LC. So what can you say about the cardinality of LC? What you have shown is L prime. So if you fix an X and as Y vary, all the X minus Y belongs to LC. Therefore, LC contains at least L prime cardinality of L prime many elements. Agree? You fix X, Y is varying over L prime and you are exhibiting elements X minus Y in LC. So LC contains at least as many elements as mod L prime, the cardinality of L prime. So we have concluded, we have proved that we have exhibited at least cardinality of L prime many elements in LC. Therefore, lambda C is bigger than or equal to cardinality of L prime. But the other property of cardinality of L prime is that it is at least this much, a power n by 1 by norm p power np. Okay. Now observe what is a power n. A power n is nothing but product of mod AV power NV as V varies over, this is my notation for Archimedean absolute values. You can check, take any number and check that A is nothing but product over the Archimedean absolute values. A power n will be nothing but product over mod AV power NV over the Archimedean absolute values. Which is bigger than or equal to from the other inequality. So already we used this inequality. Already we used this inequality. And now we are using this inequality. Mod A is bigger than or equal to CV by 2C naught. Mod A is bigger than or equal to CV by 2C naught. CV by, so mod A is bigger than or equal to CV by 2C naught. So product CV by 2C naught power NV, which is strictly bigger than C1 product CV power NV. You choose a C1. So what is the constant here? The constant here is 1 by 2C naught power NV. Take a C1, that's a positive number. Take a C1 which is strictly less than that constant. C1 is positive and strictly less than that constant. So you got this is bigger than C1 times product CV power NV, which is equal to C1 times product V in S infinity. This was the definition of norm C. Norm C is CV power NV. So you got this at, for some positive constant C1 at the Archimedean places. If V is non-Archimedean, they will correspond to some prime ideal P, and then CV power NV is nothing but 1 by norm P power NP. This you can check. This is easy, almost the definition, and therefore this product corresponds to the non-Archimedean valuations, and therefore the full product lambda C is strictly bigger than C1 times the product over all V of this, which is by definition the size, the volume of C. So you've got lambda C is bigger than C1 times norm C, which is what we wanted to prove. Okay, so this is the result. And this is a counting argument. We have given upper bound and lower bound for a certain infinite box, the number of global elements inside that infinite box, number of field elements inside that infinite box. We defined a notion of a volume of that box, and we counted number of elements and gave good bounds depending on two constants. Constants are absolute constants depending only on k and nothing else. It does not depend on the MK divisor. Okay, and this will play a role in the proof of Dirichlet's unit theorem. So let's stop here and discuss a little bit and then stop. So I can stop the recording.